So in this paper, we present a theory-informed RTD exploration of shape-changing artifact, transTexture lab. So what is transTexture? TransTexture is a digital device featured with a deformable lab-shaped surface. So input interface of deformable is a wooden knob on its top surface, and the output device of deformable is a stepper motor, and which can trigger an embedded mechanism to deform the elastic fabric. So deformable and shape-changing artifacts refer to physical changes in material forms as inputs or outputs of computing. So however, the manifested materiality may pose challenges when it comes to designing a deformable device, so which describes dynamic relationships between practitioners and computational artifacts during the process of reaching physical and digital materials. And Rasmussen and his colleagues suggested adopting design-oriented approaches for more in-depth discussions on materiality during the process of crafting shape-changing artifact. For this study, we have two main research goals. We want to contribute a theory-informed perspective on the practice of designing for long-term experiences with deformation. We also aim to connect compositional interaction design concepts into key design decisions for supporting lived experiences with dynamic deformation over time. So what is compositional interaction design? It refers to the act of designing interactions by bringing together different materials into composition that will enable that particular interaction. So this concept provides a repertoire to guide the process of attending to very short-temporal and functional qualities of computing. So as a result, Wiberg claimed, so it can be important to have a set of models of interaction design compositions in mind when starting up a new interaction design project. So experimenting and selecting materials involve explorations of how the activation of one physical material or substance can be used in the further activation of other materials. Integrating composing and crafting with materials refers to programming with materials by bringing software and hardware together. At this stage, the pieces are put together into a functional and compositional whole. Engaging in the activities of discussion and reflections focuses on thinking through the whole project to understand what can be learned from it and what can be taken away for the next project. So we attended to a dynamic physical form with materials at hand by experimenting with and selecting materials. And we 3D modeled a mold to test the deformability of casted silicon pieces. While the silicon-made lab shade can support long-lasting interactions, the casted lab shade pieces require a large force to deform its surface. So this problem stimulated us to adopt the elastic fabric to manifest deformation that are softer than the silicon material. So while the elastic fabric can sustain like repetitive deformation over periods, and there was a need to craft an actuation mechanism to deform the selected fabric. So we considered the mechanical structures were durable for haptic engagements because they have more widely applied to everyday computational objects, such as So we utilized the CAD software to model the mechanism with which we can configure digital materiality on the screen to design aesthetics of physical material forms inspired by a gear can expansion mechanism. We digitally disassembled the 3D model of the mechanism to learn the mechanical principle. We wanted to understand how the limitations of the mechanism may affect engaged interactions with deformation. Yet the early 3D printed mechanism was not selected for further composition because the fragile parts could not resist haptic interactions. So this challenge motivated us to redesign the mechanism to support engaged relations with deformation aesthetically and organically. We wanted to craft a reliable dynamic form that can support lived experiences over time. So to manage stresses on the form, we conducted a finite element analysis by applying different factors to the mechanism in a simulating software and reflecting on our first-hand insights motivated us to add texture patterns to the actuation boards, and which may augment the manifestation of dynamic deformation. So keeping the overarching goal in mind, we aimed to add layers to enhance everyday interactions with deformation. So we found that NeoPixels created a high degree of softness and a long life level suitable for an everyday artifact. So in the end, we selected a LED ring with 12 NeoPixels and to further explore how together with the white contrast fabric. So we instantiated the transTexture's materiality of interaction as a computational whole by integrating composing and crafting with materials. And the materiality of interactions describe intervened processes between the threads of interaction and the threads of computing. So as the temporal form can trigger richer experiences with the static form, we added this feature to transTexture by programming with different actuators. So initially, a stepper motor was leveraged to actuate the mechanism, so which can trigger deformation as an output device. So if we can alter the loop limits to provide a full 380-degree rotation, people may have more time to experience the temporal fall between a series of computing of rotating the loop and a series of deforming the fabric. So we tested the early prototype in team members' homes for around 2 months to enhance the actuality of transTexture. If people are more willing to live and interact with transTexture, so they will have more opportunities to experience dynamic deformation over time. So specifically, each teammate tested the material deformable and the temporal properties of transTexture. However, so for most of us, and there were fewer direct interactions with transTexture as time went by, and these insights lead us to replace like the visible and touchable parts, and that were made of ABS plastic with natural and painted wood as a way to materially invite more ongoing haptic interactions. So we adopted the 3D rendered software application to explore alternative materials for transTexture, and we could explore possible combinations by applying different wood types to the digital model, and our endeavors resulted in the adoption of solid wood to fabricate the rotary knob and the base of transTexture, and the wooden materials non-conductive and heat isolating properties, like safely protected the installed electronics, and the materiality of wood helped to sustain the long-term experiences we sought. So ultimately, we mass-produced 3 sets of transTexture labs by composing electronics, physical parts, and the mechanism together as a computational whole. So we derived the insights for further explorations on composing computational wholes by reflecting on the design process and the approach. So we consider developing creativity in materiality may benefit the compositional interaction design, so which refers to the increase and decrease of substrates across the design process. Developing creativity in materiality across the design process may open up more design opportunities. Developing creativity in materiality across compositional thinking and making may benefit to derive first-hand insights on temporal properties of materials. We also found configuring temporal expressions across compositional design process is crucial for instantiating a particular form of materiality. So designing diverse ways to express temporal form may enhance the manifestation of materiality. Adding a waiting time to express temporality of computing may shape long-term relations with the instantiated materiality. So in terms of the materials and forms, and selecting the materials with robust and translucent properties may contribute to frame long-term relations with designed material forms. Weakening the manipulability of composed of computational wholes may augment the manifestation of materiality. Highlighting portable features may trigger richer experiences with the compositional wholes. We also reflected on the proposed repertoire of composition interaction design. So further research can model and simulate materials to integrate longevity into materiality. Specifically, design practitioners can experiment with materials in the early phase of design implementation process, and they can develop platforms for advancing material modeling and simulating progresses, and they can also construct more tools to enrich material modeling and simulation in more immersive ways. So living with materials can blend actuality with materiality. So further work can adopt the first-person approach to test the actuality of design artifacts during material simulation processes, and grounding design implementation in real material context may establish credibility to the instantiated materiality of interaction.